In the last lecture, we talked about the dot product. The dot product gives you a constant or a scalar, so there's another name for that. It's called a scalar product. In this lecture, we're going to go over another type of vector operation. It's called the cross product. The cross product will produce a vector, therefore there's another name for that. It's called the vector product. So hopefully after this lecture, we will be able to calculate the cross product of two given vectors. And there is a method that we're going to apply to do the calculations. It's called the determinant approach. And at the end, hopefully we will be able to understand the way to find a vector orthogonal to two given vectors. So I'm going to give you the definitions or the geometric representations of the cross product first. And then we're going to do some basic calculations to get to the idea of the cross product. And then later on, we're going to jump into the details of how to obtain the vector from the vector product or from the cross product. So the first definition is that if you are given two non-zero vectors u and v in R3, the cross product or the vector product denoted as u crosses with v is a vector with the magnitude of u crosses with v equal to the magnitude of u crosses the magnitude of v times psi of the angle between the two vectors u and v. So when you look at the formula and you compare with the formula we got from the scalar product or from the dot product, the difference is that for the dot product we have cosine of theta, and for the vector product we have psi of theta, where theta is the angle between u and v, and we're going to make the restrictions for theta very similar to the case of the dot product, that is theta is between 0 and pi. So now when you calculate the cross product, the directions of the cross product u crosses with v is given by something called the right-hand rule. So when you put the vectors tail to tail and let the fingers of your right hand curl from u to v, then the directions of the cross product is the directions of your thumb. And the cross product is going to be orthogonal to both u and v. And it say that when the cross product is equal to the zero vector, the directions of the cross product is undefined. Then furthermore into the geometric representations of the cross product. Now given two vectors u and v, again these are the two non-zero vector, and we just want to look at the vector in three-dimensional case. Then the vectors u and v are parallel. So the vector u and v are parallel. So when you talk about two vectors parallel to one another, that is, the two vectors can form an angle of 0 degree or 180 degree. So because we cannot really specify what kind of angles that's going to be, therefore when the cross product is equal to the zero vector, then we just say we cannot really identify the directions yet. Right, but we just know that the two vectors are parallel to one another. So the two vectors u and v are parallel in the case of theta equal to 0 or theta equal to pi, if and only if the cross product is equal to the zero vector. Now the second geometric representation of the cross product is that if u and v are two sides of parallelogram, if that is the case, then the area of the parallelogram can be calculated using the definitions that we see earlier. This particular information is right here. So the area of the parallelogram is calculated as, so you have the magnitude of u cross the square root of v equal to the magnitude of u times the magnitude of v times sine of the angle between the two vectors. So here is the situations where you can actually calculate the area of the parallelogram given the two vectors are the side of a parallelogram like this. So you have the vector u in this case, vector v is in red, and the magnitude of u is written like this, and the magnitude of v is here, and we call the angle between two vectors theta. So this is the height of a parallelogram, and this is the base of the parallelogram. So the area of the parallelogram, so area is equal to the base times height. Again, this is just the regular multiplications right here. So the base is the magnitude of u, so you get that. So the magnitude of u, and the height can be calculated as follow. So as you can see, this is the right triangle, so the height related back to the angle of theta using sine of theta. So you have sine of theta is equal to the opposite, which is the height that we're looking for, divided by the hypotenuse, which is the magnitude of the vector v. Therefore, when you solve for the height, you get the magnitude of v multiplied with sine of theta, and then you're going to bring this result back to our formula to calculate the area. We get that the base times height, where the base is the magnitude of u and the height is the magnitude of v, times sine of theta. So as you can see, the area of the parallelogram is equal to the exact formula of the magnitude of the cross product. Therefore, we conclude that the cross product, the geometric representation of the cross product is that the magnitude of the cross product can be used to calculate the area of a parallelogram. Now we're going to use this formula to calculate the following example. So we want to find the magnitude and the directions of u cross the square root v, where u is equal to 1, 1, 0 and v is equal to 1, 1 square root of 2. We don't know the details of the calculations to get the vector from the cross product. However, at this point, we know how to calculate the magnitude of the cross product. So that is the magnitude of u cross the square root of v equal to the magnitude of u times the magnitude of v times sine of the angle between the two vectors. So the magnitude of u is calculated as follow. This is equal to the square root of 1 square plus 1 square plus 0 square, so this gives you square root of 2. The magnitude of v is calculated as square root of 1 square plus 1 square plus square root of 2 square, and it's going to give you square root of 4 or 2 for that matter. Now, what about the angle between the two vectors? So when you look at the image right here, so the angle is theta equal to pi over 4 is given to us already. With those informations, we're going to go back to our formula of the magnitude of u cross the square root v. You get the magnitude of u is square root of 2 times the magnitude of v, which is 2, times sine of theta, which is pi over 4 in this case. And you get 2 times root 2 times root 2 over 2, and the result is 2. So the magnitude of the cross product is going to be equal to 2. Now for the second part of the questions, they ask you the directions of U crosses with V. Again, later on when you calculate the cross product, we're going to know the exact locations of the vector U crosses with V. But at this point, the information that we can get is that we can use the right-hand rule to determine the directions of the cross product. And from the right-hand rule, this is the cross product. So this is U crosses with V. And the property of the cross product is that it will be orthogonal to both the U and V. U crosses with V is orthogonal to both U and V. Okay, again, orthogonal means perpendicular. So this is just a quick example how to determine the magnitude of the cross product and kind of the directions of the cross product. And we're going to move on to the properties of the cross product. There are a few different properties here that we may want to look at. So given three vectors u, v, and w, and also a scalar c, the first property we want to look at is called the anti-commutative property. Why anti-commutative? Because when you calculate the cross product u crosses with v, this is not going to be equal to v crosses with u. It's actually equal to negative of v crosses with u. So when you switch the positions of u and v in the cross product, you will have different results. So that's why the anti-commutative property. Okay, so you have to be careful. The order on which you perform the cross product matters. And because of that, the next two distributive properties are quite important in the way that you write the results. So first, if you have three vectors u, v, and w, and you want to perform the following calculations, that is u crosses with v plus w. Now, as you can see, u is on the left-hand side of the cross product. So therefore, when you do the distributions, u has to be on the left-hand side of the cross product. So now you get u crosses with v plus u crosses with w. When you do the distributions, you can see u is on the left-hand side of the cross product. Here, u is on the left-hand side of the cross product. So I call this the left-hand distributions. Now, the second distributive property is when you have u is on the right side of the cross product. That is v plus w crosses with u, then this is equal to v crosses with u plus w crosses with u. And again, u in this case on the right hand side of the cross product, therefore I call this the right hand distribution. Next property, we have multiplication by a constant. So if you have a cross product and you want to scale it, you do c times u crosses with v. So this calculation is equivalent to scaling the vector u first and then the resulting vector crosses with v. Or if you want to scale the vector v first and then apply u crosses with the resulting vector later, then you have the same results. Now for the cross product of the zero vector, if you do u crosses with 0, then this is equal to the zero vector. However, this particular calculation, it has a commutative property, so that is 0 crosses with u also produce a zero vector. So this is the only situations where the commutative property apply. Every other cases, the anti-commutative property will apply for the cross product. Now, if you perform a cross product of a vector with itself, what you got is a zero vector. So u crosses with itself is equal to the 0 vector. So these are the properties of the cross product that you may want to know. Later on, we're going to do some calculations and we'll experience these properties a little bit more. Now we're going to do some cross product on the standard unit vectors. Again, the standard unit vectors consists of three vectors, I, j, and k, because we are considering three-dimensional vectors only. So the cross product of the standard unit vector I, j, and k can be useful for simplifying some calculations. And you have that I hat crosses with itself equal to 0. So for this calculation, we take into account the idea of the cross product of a vector with itself. So this is a vector and crosses with itself, therefore is equal to 0. And this is true for j hat crosses with itself, this is equal to the 0 vector, sorry. And k hat crosses with itself also give you 0. When I crosses with j, you have k. When you switch the order of the vectors, you get j crosses with I, give you negative k. Now when you do j crosses with k, you have I, and switch the order of the vector, or k crosses with j, you have this to be negative I hat. And for the last one, you have k crosses with I, give you j. Again, when you switch the order of the vectors, you do I crosses with k, give you negative j hat. And these calculations can be seen here in the three-dimensional space. And this result that we have right here can be summarized into this circle. Okay, so you have three vectors, or you have three standard unit vectors, I, j, and k. And you have the arrow here indicate that is positive directions. So when you do I crosses with j, you get k. When you do j crosses with k, you have I. And when you do k crosses with I, you have j. So that is I crosses with j, give you k. J crosses with k, gonna give you a positive I. And k crosses with I, give you positive j. And if you go the other way around, or you rotate clockwise, then you have a negative result. That is, when you do k crosses with j, you have negative I. J crosses with I will give you negative k. And I crosses with k will give you negative j. Okay, so hope that's helpful to you to look at this particular picture. Now let's do some calculations here. We want to find the result of this following cross product. So I crosses with j crosses with k. So you want to perform anything inside the parenthesis first. So j crosses with k. So j crosses with k will give you positive I. So this is equal to I crosses with itself. So it will give you a 0 vector. Now for example 3, you have the following cross product. Again, perform all the cross product inside the parentheses first. So I crosses with k will give you positive k. And k crosses with I, right here, k crosses with I will give you positive j. And k crosses with j, you go the other way around, so you have negative I. So hopefully that is easy enough of calculations for you to follow.